Florian, you should stop.
Yes.
Thank you.
Yes.
So the next speaker is James Rodi, who I was listed to be here, but obviously is not. So thank you. Go ahead.
Thank you. Okay. Can see my screen?
Yep.
Let's see.
Yep, works.
Good. Thank you. Okay. I'm James Rodi from the National Institute of Astrophysics in Rome. I'd like to thank the organizing committee for the opportunity to present. And I'd like to talk about the hard X-ray, soft gamma ray behavior of the soft X-ray behavior of the microquasar MAXI J1535 -571. On my talk, I'll give a brief overview of the characteristics for the two instruments that we used, the MAXI GSC and integral SPI. And then I'll give some background about MAXI J1535 and show a couple of the light curves during our observations. And then I'll go through some average spectra that are about 2.5 day average, just to get a qualitative look at how the source evolved during our outburst. And then I'll look at the spectra on some shorter time scales to get a better idea of what things looked like. And then I'll show the soft gamma ray light curve to try and understand some of the high energy behavior. And then I'll wrap up with some conclusions. So for our low energy observations, we used the MAXI gaslit camera, the GSC. The experiment was installed on the space station in 2009. It's got a wide field of view of and sees about 85% of the sky every orbit and covers the 2 to 30 keV energy range. For our high energy observations, we used integral SPI. Integral was launched in 2002, and it's currently has about a 2.5 day elliptical orbit. And SPI has a 16-degree fully coated field of view and covers 20 keV up to about 8 MeV. So MAXI J1535 was first detected on September 2nd, 2017 by the GSC and stayed active for about 200 days. In the soft X-rays, it had a peak intensity of about 5 crab. And with SPI, we can detect it significantly above about 100 keV on a roughly 3-hour time scale. So it was a pretty intense outburst during our observations. We got the light curve here for the 2 to 4 GSC light curve in red, the Swift BAT 15 to 50 in purple, and then the SPI 25 to 50 light curve in black. And so we've just demarked where there are straight state transitions based on the MAXI GSC paper. And so you can see the hard and soft X-ray light curves here kind of go unrelated until we get this interesting feature here about 5815, where the soft X-rays shoot up and plateau, and then the hard X-rays start to decrease. So there's a rebrightening here in the hard X-rays that doesn't show up in the soft X-rays. And so for our average spectra, we fit the 2 keV up to 500 keV with a joint fit between the GSC and SPI. And the normalizations here are just arbitrary, so we can see the shape evolution. And so we start with our first observations, excuse me, in black. And we start with strong compensation here. And there's a hard tail here, a high energy component that dominates above about 150 keV. And as time goes on, there's less, compensation's less strong, but we still have this high energy component. And then in our purple observations, it's kind of a mix where we've got compensation in this component, but there starts to be a disk black body. And then by our last observations, it's a disk black body and then a power law up to about 200 keV. So then we broke out our spectra into about a 3-hour time scale. And because of a lack of exposure time with GSE, we fit just the speed data to a CompTT plus a power law model, a cutoff power law model. And so because the electron temperature and tau are degenerate in the CompTT model, we then tied either the optical depth or the electron temperature and then left the other parameters free. So you can see in the case where we tied tau and left KT free, that you see an evolution of the electron temperature from about 31 keV. It decreases. We've got a data gap from a solar flare, and then decreases some more after the gap. And then what's termed a transition state by the GSC team, we see a flattening of the electron temperature. And when we tied together the electron temperature and let tau vary, you see a similar behavior from 1.2 to 0.65. So from there, we took the same data and did a spectral decomposition of the 100 to 400 keV, which covers the range from where the high energy component starts to become the dominant component. And so the black data points here are the total flux. The green data points are the cutoff power law fluxes, and then the red data points here are the CompTT fluxes. And so you can see during the outburst that the CompTT flux shows significant evolution from quite high down to this low, relatively flat period, while on the other hand, the cutoff power law flux stays fairly flat quite until about MJD 5816, where we see the short dip and then a return and the hints of a decrease before the sources transition back to the soft state. And so to wrap up, MAXI J1535 went into outburst in September 2017 with a peak of about 5 crab in the soft X-rays. Our hard X-ray spectra show an evolution of KT and tau during the hard state, where there's a flattening by the time it gets to the transition state. We see in our spectral decomposition that's the hard tail flux is mostly constant, while the Comptonized flux varies. And the flat light curve from our cutoff power law flux is interesting. It's similar to the optical IR flux from Balio et al. That sees a flat flux here that they attribute to an optically thin jet. And so there's a data gap, unfortunately, from 58012 to about 17 that misses some of our data, and we miss a data gap of not quite a day here. But with the results from Balio et al., and then our lack of correlation between hard X-rays and soft X-ray, soft gamma rays, we think our results instead interprets the high energy component as being related to the jet. So thank you. Any questions?
Thank you. Are there questions? I don't. I see one in the room here. I don't see any online.
Okay.
But hang on. Okay, here you go. I think the mic is on.
Is it on?
Yeah.
Okay. So I was wondering, so in 1535, the compact jet was seen to shut down around September 17th. So I was wondering if you could say a bit more about what's happening to the X-ray spectra right before and right after that date.
So the hard X-ray spectrum, yes. So let's see. Yeah. So maybe we can look at the the hardness intensity diagrams. Maybe that's the easiest place to start. So this green line here should be about where the compact jet starts to shut off. And so you can see the softening in the X-rays. In the hard X-rays, we don't really see a whole lot until several days later, but we see an increase in hardness, at least for the soft gamma rays. So we've got the 50 to 100 keV over 25 to 50 keV hardness in the third panel, and the 100 to 400 keV to 25 to 50 keV hardness in the bottom panel.
Okay, so there's so there's a small change, but nothing dramatic.
Yeah, I would say so, yeah.
Okay, thank you.
Okay, thank you. I don't see any other questions, so let's thank the speaker again.